chapter is the nuclear physics. So in nuclear physics, we have to discuss mass of proton, mass of neutron, mean the mass of nucleus. Now do remember, if proton and neutron are outside the nucleus, mass of proton or neutron outside nucleus is called rest mass. It is represented by m naught, and the value of the m naught is 1.67 into 10 power minus 27 kilogram. But when proton neutron is the part of nucleus, mean in the form of nucleon, mass of the proton or the mass of neutron inside the nucleus, mean as nucleon, it is called atomic mass unit and just represented by U, small u, and its value is 1.66 into 10 power minus 27 kilogram. Look, there's a difference, 1.67 and 1.66. Now this difference of the mass, delta m, which is m naught minus u, this is called mass defect. This difference of the mass is very, very small, but on the atomic scale, it is too large. So the mass defect is the mass of the proton, neutron outside the nucleus minus the mass of the proton, neutron inside the nucleus. This delta M is the mass defect. Now AMU mean atomic mass unit. U, this definition is, it is defined as being equal to 1/12 of the mass of a carbon-12 atom. Mean one atomic mass unit, mean 1 U is equal to 1/12 of mass of carbon-12, which is equal to 1.66 into 10 power minus 27 kilogram. But do remember, the mass of the proton is approximately 1.007276 U, and the mass of neutron is 1.008665 times U, and the mass of the electron is very small as compared to the U, approximately 0.000549 U. Okay, now the mass deficit or the mass defect of a nucleus is the difference between the total mass of the separate nucleons and the combined mass of the nucleus. So this is the definition of the mass deficit or mass defect. Now this difference of the mass is converted into energy by this formula, E is equal to mc square. Now suppose the difference of the mass is 1 U, then 1 U mean U is 1.66 into 10 power minus 27, speed of light 3 into 10 power 8 and square. So we will calculate the energy. So energy produced by 1 U mass deficit is equal to. Okay, so the multiplication of this is 1.5 in 10 power minus 10 joule, but 1 electron volt is equal to this. So when divided by this, we will get this answer. So 1 U mass deficit will give you 931 mega electron volt energy. And the next is within the nucleus. There are strong forces which bind the nucleon together. And this energy the energy required to hold proton and neutrons together is called binding energy. Now, if the nucleus is stable, it has little or no tendency to disintegrate, no decay. If the nucleus has high stability, stable nucleus, so it has less decay, mean it has large binding energy. But any nucleus which is least stable, unstable, it must be radioactive, it has tendency to decay because it has small binding energy among the nucleons. So stability. Stable nucleus has large binding energy, and the least stable has small binding energy. Now the question is, what is the binding energy? It is defined as binding energy is the energy equivalent to the energy of the mass deficit or mass defect of the nucleus. It is the energy equal to the energy produced by the mass deficit of the nucleus. It is also the energy required to separate to infinity all the nucleons of the nucleus completely. So actually, binding energy is the energy which is equal to the energy of the mass deficit of the nucleus, and the energy required to separate all nucleons up to infinity completely. I repeat, when two protons or two neutrons are joined together to form the linear nucleus, binding energy is released. So any element, any nucleus which is formed after the release of the binding energy is called stable element, stable nucleus. If the binding energy is released along with the nucleus, then it is called stable. For example, this is the X. After the decay, Y is formed and some energy is released, then this Y element is more stable than X. So after the release of the binding energy, element, nucleus, atom become more stable. Now the stability of any nucleus depends on not on the total energy, which is released. It depends on the binding energy per nucleon. Binding energy per nucleon mean how much energy is shared by the each particle during the formation of the atom. So when we will draw the graph between the size of the nucleus, mean the mass number A, and the binding energy per nucleon, then the graph is almost like this. So this first atom is the hydrogen with mass number 1, and this is the most stable element, atom, and it is iron, and its mass number is 56. Not 50, 56. So mass number greater than 56, they are unstable because their binding energy per nucleon is smaller than the maximum. And here, the mass number less than 56, they are also unstable due to the less value of the binding energy per nucleon. But the reason is, in this case, this X portion, if the element is losing mass, it is getting more stability. And here in this Y region, if the element is gaining mass, it is gaining stability. So if the element loses mass and gains stability, then the process is called fission. And if the mass is gained by the element for the stability, then it is fusion. So elements with mass greater than 56 over here, they will have fission process, and the mass less than 56 element will have the fission process. Now, if the same mass is deficit, for example, this is 2U here, this is also 2U here. Look, this rise is small and this rise is large, mean the gradient of the y is greater than the gradient of the x. So the fission is less energetic as compared to the fusion, because fusion gives more stability as compared to the fission. And do remember, this fusion is approximately mega times more powerful than a fission. If 1U mass defect during fission and then 1U mass defect during fusion, then less energy is released, and here the more energy released. So this is more powerful and this is the less powerful. So the nuclei or the atom with mass greater than 56, they are called natural radioactive. And the element with mass less than 56, they are called artificial radioactive. So fusion and fission. If the mass is more than 56, fission process for the stability, and less than 56, so fusion for the stability. The most stable element in the world is iron, and its mass is 56. Greater mass than 56, greater than iron, natural radioactive, so they will get stability by fission. And mass less than 56, less than iron, they are artificial, and they will gain stability after gaining mass. And this is artificial radioactivity, and the process is fusion, and the fusion is more powerful because in fusion we have to fuse them together. So more energy is required to overcome their repulsive forces. Otherwise, hydrogen will repel each other, but we have to overcome the repulsion. So for the fusion, H11, we have to form the helium He24. So the more energy is required in the fusion because we have to overcome the repulsion of the D2's nuclei, positive. But in the fission, they are heavy enough. They are unstable. Like uranium, one neutron is bombarded, it is divided into two nuclei, barium and krypton, some energy released. So no energy is required for the fission, but the energy is required for the fusion to overcome the repulsive forces. So this is the natural process, and this is the artificial process, because we have to arrange some type of the energy to overcome the repulsion, but it occurs naturally.